In this video, we're going to go over section 11.2 from our textbook, which is on the law of cosines. So in the last lecture video, we went over the law of sines and how to solve a non-right triangle using that law. And so we'll do something similar with the law of cosines here. We're going to start with the derivation of the law of cosines. So if we have an oblique triangle, ABC here, and if we were to draw a perpendicular line to this line segment BC here, notice that we form a right triangle ADB. Now in this right triangle, our hypotenuse is going to be C here. And so if we wanted to find sine of this angle B, this would be our opposite side, so y over our hypotenuse C. And similarly, if we were to take cosine of this angle B, this would be our adjacent side x over our hypotenuse C. Now solving for y and x respectively, notice that y is going to be our vertical component and x is our horizontal component for this point A here. Now we just found that y is equal to c times sine of b and x is equal to c times cosine of b. So the coordinates of this point here are going to be exactly that. Now notice that the coordinates of this point C here is going to be a comma 0. A is going to be our horizontal distance and 0 is our vertical distance. We're not going anywhere, we're just on the x-axis. So if we wanted to find this length of this side B here with that given information, we can use our distance formula. So if you remember the distance formula, is given by the following. So we have this here. So if we have some points, let's say x1 and if we have points x1 and y1 and x2 and y2, then our distance formula, so the distance between these 2 points is going to be x2 minus x1 squared plus y2 minus y1 squared. So that's the formula we'd use if we wanted to find the distance between these 2 points. So notice that this length b here is going to be the distance between this point A and this point C. So if we use the distance formula, we get this here. This will be our x2 minus our x1 plus our y2 minus our y1. Now simplifying this a little bit, we end up with this case here. We end up with b squared equaling this guy. So this result is one form of the law of cosines, and if we replaced a or c at the origin, or placing a or c at the origin would have given the same results, but with the variables rearranged. So this brings us to the law of cosines here, which says the following. In any triangle ABC with sides A, B, and C, this holds. And so we can use this information to solve a non-right triangle. And so let's do exactly that here. So what we want to do is we're given this triangle, and we want to find the length of the unknown side A using the law of cosines. So if this is side A here, then this will be angle A. Then this will be angle B and C here. So this will be side C, and this will be side B. So what we want to do is find this angle A using, this side A using the law of cosines. So going back to the law of cosines here, notice that this side A squared is equal to this here. Now we have our side B and our side C as well as this angle A. So we have all of the given information we need to plug in and then get our length A there. So we're going to plug in that exact information. B is equal to 9, so this will be 9 squared. C is 24. And then our angle A is 60 degrees. So we just plugged in that given information here. So A squared is going to be equal to this here, and then we know cosine of 60 is going to be 1/2. Now simplifying this, we get a squared is going to be equal to 441. Now to get a completely alone, we'll take the square roots of both sides. This tells us that a is then going to be equal to 21. So this length here will be equal to 21. Alright, now we come back to the naming convention when we're given certain pieces of information about our triangles. So for this example, we want to determine whether we have this information given and decide whether the law of sines or the law of cosines should be used to solve a triangle in this instance. And so if you remember from the last video, this naming convention is, for example, it's the information given. So for example, this would represent us given a side, an angle, and an angle. This would represent us given an angle, a side, and an angle. So this side would be in between two angles, and so on and so forth. Now, for this example here, we're told that we're given these two side lengths and this angle here. We want to figure out which one of these is given. And it might be a little confusing at first because we do have two sides and an angle, and there are several different versions of that. So I'll illustrate this by drawing a triangle and labeling it. So if this is our angle A here, then our side length A is going to be directly opposite of this angle A here. This is our angle B. Our side length B is going to be directly opposite of this angle B here. And lastly, if this is our angle C, this will be our side length C there. Now notice we are given side length A, B, and our angle C. So we're given A, B, and our angle C here. Now the way this information is given is we do have two side lengths and an angle, but we have two sides with an angle given in between. So in this case, the naming convention of the information given would be SAS. These were given a side, an angle, and a side, and our angle is in between our two side lengths. So I'll write that here. So we have one angle included between two sides of a triangle. So that's how we decide which one of these that we're given. And then for part B here, we wanted to determine whether the law of sines or the law of cosines should be used to solve this triangle. And in this case, we would want to use the law of cosines. And this is just based off of the information that's given. At first, you might say that we can use the law of sines. We have our side lengths A and B, and we also have this angle C here. So maybe what we want to do is solve for this side length C. We can do so maybe with this ratio here, using our law of sines. So we could solve for the side length C here and then plug in our known information, our given information. We know our side length A, and we are also given our angle C. But notice we don't have a measure for this angle A here. So in this case, we have two unknown values, this side length C and this angle A. So we wouldn't be able to solve or find our side length C given just this information here. So this is why the law of sines in this case fails. Now notice we have our side lengths A and B and our angle C. So going back to our law of cosines, notice if we wanted to find our side length C, we have that exact given information, our side lengths A and B and this angle C here. So we'd plug in our known values and solve for C to get that side length. So in this case, that's where the law of cosines would come into play. And so this example brings us to this nice little chart on the summary of the type of cases that we'll see. So for example, if we had the case where we were given a side, an angle, or a side in between two angles, this is the suggested procedure for solving. First, we'd find the remaining angle using our angle sum formula, and then use the law of sines to find the remaining sides. And then we also have a suggested procedure for these remaining cases as well. So we won't go through each one of these, but this is a good kind of guideline for solving these triangles. All right, so let's get into the next example here. We want to solve this triangle using the law of cosines. So in this case, we are given this angle and these two side lengths here. So we have an angle in between our two side lengths. So the first thing that we'll do here is we'll solve for this side length A, because in this case, we have our side lengths C and B and this angle A here. So we can use the law of cosines, which says A squared is going to be equal to B squared minus C squared minus, or sorry, this should be plus C squared, minus 2 times B times C times cosine of our angle A. Now, we'll get A squared is going to be equal to this guy here. And to get A completely alone, we'll just take the square root of both sides. And so this tells us A is going to be equal to 14.16. And then for the purpose of this problem, we'll just round this to 14 here, since we're dealing with whole numbers with everything else. Alright, so we found our side length A. Now what we need to find is this angle C and this angle B here. So we can still use our law of cosines to do so. Remember this formula here. Our side length B squared is going to be equal to this here. Now what we can do is solve for cosine of B here. We can do that by adding this term on both sides. So we'll end up with this on the left-hand side, and then A squared plus C squared on the right-hand side here. Now, the next thing we'll do is we'll subtract B squared on both sides of our equation here. We'll end up with 2AC times cosine of B is equal to this here. And then we'll divide by 2AC on both sides to get cosine of B by itself. So cosine of B is going to be this here. So what we can do is plug in this information. We have our side lengths A, B, and C. We'll have 14 squared plus 21 squared minus 8 squared on the top. And then 2 times 14 times 21 on the bottom. Now plugging this into our calculator, we get approximately this here. Now, if we want to get B completely by itself, what we'll have to do is take arc cosine on both sides of our equation here. So B is going to be equal to arc cosine of this guy here. And then plugging this into our calculator, this will be approximately 12.84, and then rounding this to the nearest whole number, this will be 13 degrees. So now we have this angle, and the only piece of information that is missing is this angle C here. Now we can use the law of cosines to find this guy, or we can use the fact that the sum of all of the angles in this triangle is going to be 180 degrees. So our angle C is going to be 180 minus our angles B and A. This ends up being 142 degrees. So we found our 3 missing pieces of information here using the law of cosines in this case. Let's do the same thing for this next example here. We again want to solve this triangle using the law of cosines. Now, in this case, we're given all 3 sides of this triangle here, so we're going to need to find all 3 angles. what we'll do is we'll find two angles and then use this fact here, like we did in the last example, to find the last angle. So the first thing I'll do is find angle A here. We can do so using the law of cosines. Now, similarly to what we did in this example here, we used this formula and solved for B in this case. We'll do the same thing for cosine of A. So performing very similar operations, we'll get that cosine of A is going to be equal to this here by our law of cosines. So what we'll do here is plug in this given information. This will be equal to this here. And then what I'll do is I'll just plug in this fraction directly into arc cosine, because we know that if we want to get A alone, we're going to take arc cosine on both sides of this equation. And then plugging this into our calculator, this will be approximately 23.5 degrees. Alright, now we'll do something similar. We'll find angle B here. From the last example, we know that cosine of B is going to be equal to this here. So we'll just plug in that information. Cosine of B will be A squared. So this will be 13 squared plus C squared minus B squared all over 2 times A times C. Now this will be equal to this fraction here. And then again, we want to get B completely alone. So we know B is going to be arc cosine of this guy. And then plugging this into our calculator, we get that this is going to be approximately 29.4 degrees. Alright, so now we have our angles A and B. And then, like I said, we can just use the fact that the sum of all of these angles will be 180 degrees to find our angle C. Doing so, we'll get that angle C is going to be approximately 127.1 degrees. Alright, so the last two examples illustrated how we can solve the triangle using just the law of cosines. Now we're going to switch gears a little bit into the area of a triangle. So if a triangle has side lengths A, B, and C, and if the semi-perimeter is going to be this guy, then the area of the triangle is going to be equal to this guy. Now the semi-perimeter is just going to be half of the perimeter. So if we're given all three sides, we can find the semi-perimeter and then plug that in as well as the lengths of our three sides into this formula and find the area of our triangle. So let's do exactly that in this example. We want to find the area of the triangle if we're given angle A is this, and our two side lengths are equal to these guys here. So, like we saw in this slide here, to find the area, we first need to find S, and to do that, we need all three side lengths of our triangle. In this example, we're just given two side lengths and an angle. So what we'll do in this case is we'll use the law of cosines to find our third side length. Using this formula here and plugging in our information, we can find our length A. Alright, so then A squared is going to be equal to 59.34, and then again we want A alone, so we'll take the square root of both sides. So then A is going to be equal to approximately 7.7 meters. Okay, so now that we have all three side lengths here, we can plug this information into this formula here for S, plugging this into our calculator, this will be equal to 13.05. Now lastly, to find the area, we're going to use this formula here, plugging in our known values for S, A, B, and C. So our area, I'm going to use this A here, it's going to be the square root of our S times S minus A times S minus B times S minus C. So we're going to take the square root of all of this here. This is going to be equal to the square root of 79.07, which is going to be approximately equal to this here. So that means the area of this triangle, given this information, is going to be 8.89 meters. Alright, so the last example we'll look at is the following here. We're told that from an airplane flying over an ocean, the angle of depression to a submarine lying just under the surface is given by this here. So this is our airplane, this is our submarine, and the angle of depression is going to be this here. Now at the same moment, the angle of depression from the airplane to a battleship is given by this here, and this is that angle. Now the distance from the airplane to the battleship is given by this, and what we want to do is find the distance between the battleship and the submarine. So we want to find this side length here. So the first thing that I'm going to do is label this diagram. So that'll be our point A, B, and C here. So this will be our side C, A, and this will be our side length B there. So then this is going to be our angle A, this will be our angle B, and this will be our angle C. So what we want to do is solve this triangle. We want to find these unknown values, and this will help us find the distance between our battleship and our submarine. So first notice that we're given this angle and this angle here. So if we want to find this angle A here, what we can do is we can take this entire angle and then subtract out this angle here. So what I mean is our angle A is going to be this here minus this angle here. And then this will be 22 degrees in 10 minutes and then 16 degrees in 30 minutes. So we'll keep this notation here using our minutes. All right. Now subtracting this out, what we can do is we can use the fact, so this is from previous sections, that 1 minute is going to be equal to 1 over 60 degrees. So this means 60 degrees is going to be equal to 1 minute. So I can rewrite this guy as 21 degrees and 70 minutes. So I'm taking away 1 degree here and then adding 60 minutes here. And the reason being is so when we subtract these guys, we don't get a negative amount of minutes. All right, so subtracting this, we will get 5 degrees here and 40 minutes. And then to get an actual decimal value for this guy, we'll use this fact here. So this will be 5 degrees, or sorry, this will be 5 and 40 over 60 degrees. And then plugging this into our calculator, this will be approximately 5.67 degrees. All right, so we have another piece of information. We have this angle here. Now notice, if you remember from the last video when we were talking about alternate interior angles, we actually have the angle for this guy here. So since this angle here, we have this 16 degrees and 30 minutes. And our angle C here are what's called alternate interior angles. Our angle C is going to be exactly equal to this angle here. Alright, so like I said, if that is unclear, go check out the last video on section 11.1, and that'll be on the last example that we did. Okay, so now we have these two angles, A and C here. We can use the fact that the sum of these angles are going to be equal to 100 degrees, 180 degrees, to find our angle B. So this will be equal to 180 minus 5 degrees and 40 minutes. We'll keep this notation here, and 60 degrees and 30 minutes. Now in this case, we want to rewrite this so that we can subtract our degrees and subtract our minutes, just how we did in this example here. And we're using this fact. So we can rewrite this as 179 degrees and 60 minutes. And so we're subtracting out these two angles here. Alright, now notice if we were to subtract our degrees here and then these minutes here, we would again get a negative amount of minutes. So what we'll do here is we'll rewrite this by taking away 1 degree from this guy and then adding 60 minutes. Alright. Doing so, we'll get 178 minus 5 minus 16. This will end up being 157 degrees. And then we have 120 minus 40 minus 30. So this will end up being 50 minutes. Alright, now if we wanted to write this as a decimal here, we can plug this value into our calculator, and this will be approximately equal to 157.83. Alright, so now we have all three angles here, A, B, and C. We have this side length here, and what we really want to do is find this side length A here. Now notice we have enough information to use our law of sines. We can use this guy here because we have all of the information. We have our angle A and B, and we have our side length B here, so we can just solve for A. So A is going to be equal to B times sine of A over sine of B. Now plugging in this information, we know our side length B is going to be this here. Our angle A we found to be 5.67. And our angle B we just found to be 157.83. Now plugging this into our calculator, this will be approximately equal to this here. And if we want to round to a whole number, it'll be this here. So that'll be the distance between our submarine and our battleship given by the side length A of this triangle. Alright, so that'll be it for this video.